Canterbury, and he's going to talk on identifying phylogenies, extending the notion of uniqueness.
I didn't get this done. So really, it's just it's a notion that sort of generalises uniqueness, but effectively it's just as good in practice. Okay, so that's what identifying means. So what you do, you've got some input, whether it's trees, characters, or sequences, and somehow the first thing you may decide is the input compatible? Compatible subject to some criterion, whatever that may be. We'll see some examples shortly. And you say, yes, it is. And the next question you may ask, is there exactly one object that satisfies this criterion? Okay. Well, so if there's exactly one, that's quite a very strong condition if it's unique. So something that's effectively just as good, here's a particular example in terms of phylogenetic trees, is my input I identifies a tree if not only is the tree consistent with the input, but any other tree that's consistent with the input is a refinement of it. And I'll do some examples shortly. Okay, so identify means not only is it consistent with the input, but any other tree that's consistent with that input is a refinement of it. So once you know, if a collection of whatever the input identifies some tree, and you've got that tree, then any refinement is as well. And so it's good enough for you to know everything about what trees satisfy that criteria. Okay, just that single object or single tree. So for example, here's an example. So my criterion here will be displaying. I've got a collection of subtrees, in this case rooted triples, and I want to know, is there a single tree that displays those 4 rooted triples? All right, and we'll bed that information. Okay, so, oops, go too fast. And the answer is yes, here is a tree that does that. Each of those 4 input trees are embedded in this tree. Okay, and so for example, the one on the left with the monkey and the mouse, all right, the path from the monkey to the mouse is separated from the path from the pig to the root. All right, and that's what display means in this particular case. Well, that's our criterion. All right, so the original set is compatible. So it satisfies our criterion of display. You may ask next, is it unique? And in fact, the answer is, in this case, there is only one tree that displays the input trees, and that happens to be this one. Okay. Or you could do it for unrooted in the same way. Here's my input set of 3 quartets. They are compatible. Here's a tree that displays those 4 quartets, 3 quartets, I can't count. All right, and again, what I mean by display is the blue quartet sits inside this tree. That's what I mean by display. All right, is it unique? Is that the unique tree? Well, it's not unique because any refinement of that tree would also display the other 3 quartets. So, for example, if I had all right, that's what I mean by refinement. I sort of pop vertices out, only going one way. I don't contract them, I just pop them out. So here's another tree, it's a refinement of that one and displays the original 3. All right, but the important thing about this tree is it actually identifies, those 3 quartets identify this tree. All right, every tree that displays those 3 quartets is a refinement of that one. Either it is that one or it's a refinement of it. Okay, so that's the notion of identify. All right, so in some sense it's a bit of a potpourri of results on the notion of identify that it talks about. So here's a problem. I've got a collection of, think of them as rooted triples if you like. All right, not only does that set of rooted triples identify a tree. So I've set it up as a decision problem, identifying rooted supertrees. I'm given a collection of rooted phylogenetic trees. Does P identify some tree? Some rooted supertree? Right, Philip Daniel was a master's student at Canterbury a couple of years ago and decided at the end of his master's to carry on but doing medicine instead of mathematics. Came up with a constructive polynomial time algorithm for actually realising that. Okay, and just as a bit of insight for why does it work, or how does it work? Well, if I've got a collection of rooted triples or rooted phylogenetic trees, how do I decide whether they're compatible? Well, one way is using the build algorithm. Okay, so those familiar. So you may have to be, yes, so in some ways you have to be familiar with what they mean by the build algorithm. All right, but there's an algorithm for doing it, and it's very simple. All right, how do you realise uniqueness? Well, what you do is you get your rooted triples, plug it through the build algorithm, If the output is binary, a binary tree, then the answer is unique. If it's not binary, then it's not unique. So it's actually quite nice, just based on the simple algorithm, same algorithm. All right. What do you do for this one for identify? What you have to do, you do the same thing, but each step you've got to do some finite or polynomial time number of checks and the iterations. So those who are familiar, it's an iterative process that keeps repeating itself. Okay, but at each step you've got to do some checks, then you go on to the next one. Do some checks, go on to the next bit. Okay, so there's an extra bit of step, but essentially the same algorithm works. Okay. Future directions. I don't know. This problem's hard. I would think hard to work out. So what about unrooted supertrees? I'm given a collection P of unrooted phylogenetic trees. Or just think a set of quartets is fine. All right. What's the complexity of deciding whether P identifies some supertree? Okay. If you replace it with uniqueness, that's still unknown. All right. And it's even unknown if it's NP. An NP. All right. Can you decide in polynomial time? Can you verify, I suppose, its solution in polynomial time? I don't know the answer to that. Okay. So there you go. There's a problem. All right. So in some sense, I've got a collection. I'm deciding compatibility, uniqueness, then identify. Let's flip the problem around a little bit. Here I'm given the tree initially. Let's say it's binary. Then the minimum number of quartets need to identify that tree. And identify for binary trees corresponds to uniqueness. All right, it's one and the same. I can't refine a binary tree any further. Okay, so uniqueness and identify for binary trees is one and the same. Well, what do you need for that? How many quartets do you need to define a tree or identify a tree? Well, it's the number of leaves minus 3. All right. Now, not just it can't just be any set of quartets of number of leaves minus 3. All right, but you can find it's very quick to find such a set of quartets. Right, so the next question is, what about non-binary? Notice the idea of identify captures the notion of non-binariness. Non-binariness, is that a word? I don't know. Okay, so you may think, well, is it n minus 3? Well, for non-binary trees, is it n minus 3 or the number of leaves minus 3? Well, some authors thought so. And yeah, unfortunately I can't remember which theorem it is, but something in the back there, and a PhD student of mine recognised the mistake first up, and it's actually in the base case is the error. All right, so you might like to go to it. I think it's in the subtree and supertree section. All right, and you can see it there. And it's not n minus 3. It's actually a lot more complicated than that. All right, n being the number of leaves. But what you have to do is you've got to run over every interior edge and look at the degree of its n vertices. All right, and do some summing over that. Okay, so T is my phylogenetic tree. Remember, it's not necessarily binary. Cardinality of a minimum size set of quartets that identifies that tree is this sum here. And just to give a flavour, is there a duster? Yep. All right, so I don't know why we thought, but apparently we did think at one stage that it was the number of leaves, which is 8 minus 3. So 5 quartets is enough to identify that tree, but it turns out to be 6 is the actual answer. All right, and what it says is you look at take an interior edge. I've only got one here. All right, look at the biggest one. That's V. So it's the degree of this vertex. So it's 1, 2, 3, 4, 5, 6. Minus 2 is 4 times. I'll do it the way it's set up there. The degree of the other vertex, minus 1. 1, 2, 3, 4, minus 1 is 3. Divided by 2. Oh, you've got some scaling function there, but you don't have to worry about it with this one. And it's 6. All right, so it's not the same. You've got to run over every interior edge. If you wanted to, you could actually, for a fixed n, you could characterise the phylogenies for which this number is minimised and which is maximised. Okay, so for a fixed n, this number is going to vary. All right, but you can actually characterise when it's a maximum and when it's a minimum. Which trees satisfy those criteria? Okay, so that's doing identify with trees. What about identifying with characters? Alright, so what do I mean by a character? So a character, I'm partitioning the set you're interested in, in this case A to F, and into various character states. Alright, so I've got an orange character state with just A in it, and the first one, I've got a red character state with B in it, a green character state with just C in it, and a blue one with D, E, and F. What's my criterion I want to do here? Well, my criterion for displaying things on a tree is that colour code the leaves appropriately, and then any leaf with the two of the same colour, you join up with a minimal path, if you like, of that particular colour. All right, and the criteria here is that these colours have got to be just pairwise disjoint; they can't meet up. All right, and the idea is to capture homoplasy free, with no convergent transitions or reversals. Okay, so that's the idea with that one, what you want to do. And so, in fact, this set of characters here is actually displayed by this tree. All right, you can run through the others in exactly the same way. Each of the characters have to do that, like this, and that exactly works. I don't know why I'm doing this slide. I am denied right up to the last minute whether I put this one in, but I'll do it anyway. So, typically the problem's hard. The compatibility problem in this case is hard. All right, so it's hard to decide whether a set of characters is compatible, i.e. can be displayed on a single tree. All right, but what you can do is you can sort of characterise it in terms of caudal graphs, and you get this really attractive characterisation in terms of a particular type of graph. I'm not going to go into, but it's a particular type of graph. All right, and it's no result date. The compatibility result for that dates back to Bunneman 1970 something or other, 4 maybe. I don't know. I'm guessing 72 or 74. And it was recognised a little bit later, and then Mike actually formally proved it. It actually wasn't never really formally proved until about 91. Okay. Well, you can also do the uniqueness in terms of caudal graphs as well. You can have a uniqueness characterisation. All right, and you can do an identify one as well, but you don't need to read it. It's not particularly attractive, but it's very similar. For those who know, it's very similar to the uniqueness one. For an if and only if, first of all, you need some phylogeny that displays the original set, plus there's some notion of distinguishing. Okay, and I'll explain distinguishing for something else in a minute. No, I won't, because I'm not going to do. I've bypassed that already. So you need a notion of distinguishing, and this extends that. And then this thing here is to do with some particular set of caudal graphs. Okay, but it's similar. It works in a similar way to the uniqueness one. Okay, so you don't need. I'm not going to go through the bits and pieces, but it works in a similar way. So what about identifying with a minimum number of quartets? We did it, with characters. We did a minimum number of quartets. So I give a tree, fix my phylogeny. What's the smallest number of quartets I need to identify it? Well, you can do the same with characters. Now, going back one step, if it's a binary tree, remember to find and identify as one and the same for binary trees. At most 4 characters suffice. All right. So you give me your favourite binary phylogenetic tree, I can find you 4 characters so that's the only tree that displays them. Okay, so that's the only tree that displays them. You can't, it says at most 4, all right, sometimes you do need 4. Okay, so you can't get away with 3. All right, and then a couple of years ago, what about the notion of using identifiers? Now you want this to go from binary to non-binary, all right? And you can get this result here. And what it's basically saying is, if you look at the bottom one, so D is take a look at your tree, look at the vertex of highest degree, all right, that's D. All right, D is your vertex of highest degree. The bottom thing saying is you need at least log D characters. All right, that's what 2 says. And what 1 says is that effectively log D characters is enough. Okay, you can find it with log D characters. And if you look at the first one, first result, if your tree was binary, then D is 3. All right, so log of 3 minus 2 is 1, so it's log of 1 is 0, and that gets you the original theorem. All right, actually gets you back the original theorem for binary trees. There's a couple other little points I put there. Oh, first thing is the proof actually provides an efficient algorithm for finding such a set of characters. All right, and you may be some quirk about the range. Well, there's 2 things here. Originally, we did the result for X trees. not just phylogenetic. I think Andreas talked about that this morning about X trees. All right, and so for a three star, if you're only looking over phylogenetic trees, you don't require any characters. Okay, so a 3 star is a tree looking like this. All right, and if you're only concerned with phylogenetic trees and not X trees with interior vertices can be labelled, then it's actually 0. But if you actually are interested over all X trees, then you require 3 characters for the 3 star tree. Okay, so doing it over X trees here, I've jumped a bit. All right, but binary trees also have maximum degree 3, but they require 4. Okay, so you're going up variations anyway depending on the degree. Okay. The other thing is it doesn't happen, I can never get the word right, monotonicity. So if you look at the, let's get this right, a 6 star tree requires less characters over all X trees. A 6 star tree requires less characters than a 5 star tree. All right, you actually need more characters to identify a 5 star tree, all right, one with 5 leaves, as opposed to a 6 star. So there's some curious things there. And interestingly, when I finished writing the talk not very long ago, be interesting to see this. If you did over phylogenetic trees, not X trees, can you say a little bit more? Okay, X trees is a lot of variation, but with phylogenetic trees, could you say a little bit more and produce slightly stronger results? Don't know the answer to that one. All right, and that in various parts, those authors all contributed. So thank you.
If you could go back to this last one slide.
Yep.
The one with this one, yeah. So the theorem, the first one, uses quartets a lot.
Yep.
And I assume you use, what are the kind of main steps for the...
I hope you were going to ask me that, Kathy. I haven't looked at that paper for so long.
Sorry.
It went to a journal, and for various reasons it didn't get accepted. And then went to another one that got accepted straight away.
I'll ask you
and
later.
I can't remember how it goes. All right.
I'll ask you later.
Yeah, but you can. The thing is, the proof does give a construction for it. Okay.
Ooh, one at the back. This is probably a really stupid question.
That's right, because I'm really stupid, so that's fine.
Nobody is actually going to use 4 characters to construct a tree. But I was wondering about like practical taxonomists actually use dichotomous keys to identify species. How efficient are they in choosing the number of questions that they ask in order to get you to them?
I don't know, but it's interesting the fact we looked at this with Mike several years ago, and originally we had a result for 5 characters. So it's interesting to note that to identify it, fix on your tree, you may think, oh, more, generating more characters and more information is good. But it's actually a surprise. It was more of a mathematically surprising result that you need far fewer than you'd ever think. All right, you wouldn't think you don't. It gets down to 4. It's all you require. All right. For practical considerations, other than that, I don't know. Okay, sorry, I just don't know. Yeah.
Okay, well, let's break for tea. We'll resume again at 3:30. But first of all, let's thank the